Hello everybody, welcome back to my channel. So in this video I want to talk about all the different projections that come in organic chemistry and the different ways that you can interconvert them. I know this is a confusing topic for a lot of people, so let's get started. Okay, so there are four major types of representations or projections. The first kind of representation is the wedge dash. So we know that carbon, when it's sp3 hybridized, has a tetrahedral shape. One bond is in a particular plane, the other is in the plane. One is, so assume that the screen you're watching this in is a piece of paper. There's a carbon atom. Two bonds of that carbon atom are in the plane, as in they go along the lines of the device or the paper. But two other bonds go outside and inside the plane, this and this. So that's how we represent this is a wedge and this is a dash. So remember that for future references this will come in handy a lot of times. The second kind of projection is sawhorse projection. So basically this we basically represented for a single carbon atom, but when we look at two different carbon atoms, as you see, this is the bond that's in plane, out of plane, inside plane. Not that you couldn't use wedge dash here, but I'm trying to say that, okay, so this is an observer. Whenever I'm talking in general sense, we'll always assume that the observer is looking at the atom or the molecule from the left side. Now when I look at this from the left side, I'll see that this carbon atom has one bond on the left, like it's going sideways, and another that's going right to me. This is a wedge bond and this is a dash. So this may not always be given to you, but you will have to remember this. Now coming to the projections that need interconversion, because this to this is I think pretty easy, because you just have to remember that wedge is on one side and dash is on the other. I apologize for the background noises, but let's move on. So from Sawhorse to Newman. See, let's imagine a compound like this. There's a CH3 here, hydrogen and a phenyl group, CH3 here, hydrogen and chlorine. See, again, like I said, we have to look at it from the left. The first carbon atom we see is a dot. Now just simply represent CH3, H is inclined at this angle, Cl is inclined at this angle. Now moving on, the second one we see is going to be a circle. So this CH3 bond is directly above. So if you're looking at it from the left, you would see that this CH3 is like, you wouldn't see the second carbon necessarily, and the CH3 would be overlapped. So just for visibility sake, we represent it slightly on the side. Slightly on the side. So that is CH3, this is phenyl, and this is hydrogen. So this is Newman projection. This is going to be the most used. This and Fisher are going to be the most used out of all these, but you will need to know the conversions. So I am pretty sure you can just go reverse with this again. Let's move on to how to convert Sawhorse to Fisher, and then we'll talk about Newman to Fisher as well. So Sawhorse to Fisher, I'll take the same example, because Fisher is actually a little bit more complicated than Newman. Same molecule. This is the first carbon atom, right? If both of these little branches, one branch is on one side, the others are on the other side, right? If both of these are on the bottom, then the first, so this is what Fisher would look like. So the first carbon atom you see will be the first here, because both of these are downwards. If the situation was reverse, like C, H, Cl and CH3, then we would have put the first carbon atom here. Okay, so because both of these are downwards, the first carbon atom has both the branches downwards, we will put it in the first, like yaha. So CH3 is over here, Cl, H, C, CH3, PH, H. So that is basically Fisher projection, but if the situation was reverse. So I'm not really talking about only this being reverse, I'm talking about both. Okay, let me explain that in more detail. You see this compound right here? For this, you would see that the first carbon atom that you see has this on the top. So now we put it in the second, not just the first. You'd see that both have their branches, little branches on the bottom. So we put the first carbon atom first. Yeah, I guess, I'm sorry, you have to observe it from the left. Now here, both the branches are on the top. So when I write the Fisher projection for this, I will put this first carbon on the second position. So H, Cl, CH3, PH, H, CH3, H, PH. So this is how the Fisher projection for this would go. Now if you're wondering how the Fisher projection would be for a molecule like give me a second, for a molecule like this, now the answer would be we cannot draw a Fisher projection for a molecule like this. We can draw a Newman projection. Like I told you, you imagine this as the dot. This is the dot and you represent H, Cl, CH3, and then this would be the circle. Again, that's a terrible drawing, but still, this is CH3, PH, H. This is how that would look. But we cannot draw a Fisher projection. They have to be eclipsed. Now, if you don't know what eclipsed means, it's basically I erased the Newman projection, didn't I? Good girl. But basically here, if you notice, the CH3 is perfectly behind the CH3. So like if I were to draw a Newman projection for this, stay with me here. So CH3 here, H here, Cl here, and then a circle, CH3 slightly just for representation, PH and H. So if you notice here, CH3, the first CH3, the CH3 of this carbon atom and the CH3 of the carbon atom behind the first one, so they are completely overlapped. This is called eclipsed form. Now eclipsed, staggered, that and all we can get into later. I just explained eclipsed because I used it. But yeah, anyway, hope you understood this and hope it cleared all your confusions regarding, projections. And do check out my channel for more JEE dropper content. Bye.